Part 3 of section 1.5. So what we're going to look at here moving forward is the shape of a histogram. And, in statistics, there's reasons why you would need to be able to describe the shape using proper terminology. And one of the main reasons is that certain statistical methods will only work for certain types of data distributions. So if the data has the right shape, you can use a certain method. If it doesn't have the right shape, then you can't. So it is important to be able to do this. And typically the shape of a histogram is based on the number of peaks, and if there's just one peak, where that peak is located. So we'll look at the first one here and leave some space above what I'm drawing here. We're going to put 6 total into this little space here, so we might want to draw these a little small. And this first one, something like this. We're going to focus first on naming things based on the number of peaks. So here I see 1 peak, and 1 can also be thought of as uni. If you ever have a unicycle or have seen a unicycle, it has 1 wheel. So here we have like 1 peak. And another term that goes along with peaks is modal. So we would say here that this is unimodal. There's 1 peak. The next one we will have, might be already able to guess. And the thing to pay attention to here is that there's 2 distinct peaks. They don't have to be the same height, but when you're describing these histogram shapes, you're looking for how many distinct peaks are there. That, again, they don't have to be the same height. And when you have 2 things, like 2 wheels on a bike, you call it a bicycle. So we're going to call this bimodal. And then moving after that, basically once you get to a point where there's 3 or more, you could say it's trimodal, if you want to get fancy. But for the most part, what you do is you just say in statistics, there's multiple peaks. So 1 and 2, they have their places, but after that, it's like, we're just going to call it multimodal. All right, so once you've talked about the number of peaks, then there's something that you need to be able to describe in terms of the location of the peak relative to the rest of the data. And really, even though we talk about where the peak is located here, the thing that's going to be telling about the shape I'm going to draw is where what's called the tail is located. So if you think of this as like some really bad drawing of an animal, the tail is out here on the left. And if you can kind of picture that there's a bunch of bars under this thing, in the tail, the bars would be really short. Not a lot of values there. So out in the tail is typically where you see the outliers. And outliers have the potential to move numerical measures that we'll see in the next chapter towards them. They pull them towards them, especially the mean. So in this case, the tail being on the left, it's going to skew the numerical measures to the left. So we call this skewed left. You always focus on the tail for describing things. Oops, I should be skewed left there. Sorry, getting away from myself. So, you always focus on that tail for describing the shape when it's not in the center. So here we have this one like this. The tail, again, is telling. The tail is on the right, so this is skewed right. That's real important to keep in mind. It's easy to look at the peak on these, but you always want to look at the tail. And then the last one, sometimes if I can draw this with any sort of skill, you have basically the same size tail on each side. It's almost like a mirror image. If you were to fold it in half, you might already be thinking of the word we would use to describe that when it's like a mirror image. Symmetric. So you could call this symmetric and unimodal. And we'll see later on in the class, there is definitely a place where symmetric and unimodal comes into play, and its symmetric unimodal graphs are actually one of the most important types of graphs in statistics, and we'll see more with that a little later in the class. All right, so this example here, basically we're going to start putting some of the stuff in play with histograms and shapes. So we have some data here for the heights of some randomly selected basketball players, and the heights are all in inches there. And then down below, want you to find the frequency and relative frequency of each class. So the thing to keep in mind with this, the 70 with the square bracket means you can be equal to 70. 74 with the round bracket means that you can go up to but not equal 74. The equal 74 goes into the second class. Up to but not equal to 78, and then the equals to 78 goes into the third class. So in this first class, you really want to think of it like 70 all the way up to 73.999999999. Okay, so go ahead and fill those in, and I will let you pause, and then I'll come back. Okay, so hopefully you paused. You might be noticing lots of numbers came up here. You might also notice the sound of a ladder being moved around in the hallway. One of our maintenance guys is changing a light bulb out there, and it's one of those metal ladders that makes a lot of noise, so I apologize for that. But at any rate, if you were to go through and count up the numbers that are equal to 70 and up to but not equal to 74, you should find 3 of those. It would be the 73, the 72, and the 72.5. For 74 to 78, there's 5 of those. So the 76 goes there, the 77 goes there, 77.5 goes there, and 75.5 goes there. 78 equal to that, up to 82. There should be 10 of those. So the 79, the 80, the 79, the 81.5, the 80.5, the 78s, they all go there, the 81, 79.5, and let's see, I'm sorry, the 76.5 should have got crossed off in that first one there. I was getting carried away. And then for the next one then, just have 2 left that are in between 82 and 86. So from there, you form your relative frequencies. You find the total is 20. 3 over 20 reduces 0.15, 5 over 20 is 0.25, 10 over 20 is 0.5, and 2 over 20 is 0.1. So now what I'd like you to do is take that information and create a histogram with frequency on the vertical axis, then describe the shape of the histogram. And I'm also going to pause this right here to give you a chance to do it. And when you come back, there'll be a picture, or if you just let it keep playing, there'll be a picture that pops up. So go ahead and pause. All right, so you should have something that looks like this. Remember that you should have a title here, basketball player heights. You should have on your axis, the vertical axis, the frequencies. You only have to go up to 10 since the max frequency was 10. And then let people know that it was frequency by putting that on the left side. Then down below, notice here, I just have a tick mark for the 70. And then I go up to 74. And it is understood in the histogram world that equal to 70 starts, and then you go up to, but stop short of 74, and then the 74 picks up for the second bar. And then 78 up to 82 picks up equal to 78 in the third bar and goes up to just short of 82 before picking up in that fourth bar. So you don't have to write those numbers, like that, and it's kind of understood that if you the left number is the equal to for the bar that comes after it. And then a label down here, let people know what those numbers mean, heights in inches. And if you look at this graph, you can see that the peak is here, and there's more to the left than there is to the right. So we'd say the tail is going out to the left, so the shape of this should be skewed left. All right, so let's go ahead and take a look at pie charts. So pie charts or circle graphs are commonly used to visually display relative frequencies. And sorry about this ladder noise here. I'm just going to pause for a second. All right, so I think the ladder is done for a second here. Sorry about that. Anyway, so they're good for relative frequencies. You probably see these things with like budgets, like how people are spending, the bigger slice of the pie is getting the most of the budget. They're a really nice visual for displaying relative frequencies. And the pie represents the entire sample. The slices represent the categories or classes. So to find the angle that each slice takes up, you just multiply the relative frequency as a decimal of that slice by 360 degrees, because there's 360 degrees in a whole circle. And the percentages in each slice of a pie must all add up to 100%. You might, if you've done some rounding, come a little short of that. I think I mentioned that earlier. If you've done some rounding, you might get like 99.9% or whatever, but you do need to be very close to 100%. So what I want you to do is look through these here and determine which one of those pie charts best represents and more accurately represents the data that we saw from example 2, those basketball player heights. Go ahead and pause. Okay, so as you're looking through these, there's the percentages there. If you did the relative frequencies, it should be real easy. And I'm looking for where the frequency of 50% matches up. I'm going to just go with the biggest slice. And that should go with the 78 to 82. And the only graph that has that is part C. And if you look at the other percentages, they do match up to those relative frequencies. So graph C is the correct graph for that basketball player height data set that we had. And then follow up here, what would the angle measurement be for each of the sectors or slices? So another fancy name here to be aware of. They will often, in a circle, when you look at the, looks like pizza slices to me, but they'll call them sectors sometimes. So just kind of keep that in mind. It's another name for the slices. So in the correct graph, the 70 to 74, once you figure that out, the angle, and then 74 to 78, 78 to 82, and 82 to 86. Go ahead and pause. Okay, and poof, there they are. So again, in order to make this work right, you're going to take the relative frequencies times 360 degrees, and you do need to convert all those relative frequencies over to decimal if you haven't already done that. So 0.15 times 360 degrees would give you a 54 degree angle for that 70 to 74. So up here in the graph, this blue region here for 70 to 74 has an angle of 54 degrees. And similar for the next. And the 25% one, you can see that orange slice. It looks like it has a right angle right there in the corner, 90 degrees. The 50% takes up half the circle. That straight line, angle is 180 degrees. And then 10% would have 36. All right, so that completes the 1.5 material. If you do have questions about it, please ask them. I can't help you unless you ask questions. And you should be, if you don't have questions, ready for the 1.5 homework.